Okay, one second. Okay, got it. So yeah, hi everyone. I'm gonna start my workshop now. That's basically an introduction to TensorFlow, and I'm gonna look at this tab, so I can't really see like what's happening there. So I'm just gonna like hopefully make sure that everyone can like follow along. So yeah, I'd like to start off with basically a personal introduction about me first of all. Then I'm gonna talk a little bit about like an overview about like what is machine learning, and then a bit more about what is TensorFlow. And then lastly, I'm going to give you like a pretty brief overview of like what exactly neural networks are so that you can have a good understanding of it before I move on to other things. First of all, a little bit about me. I'm currently a software engineer at Amazon, where I work on the Alexa devices team. I work on like ML and like Android apps for things like or your usual Alexa devices like the Echo Show 8. I'm also working in grad school at the University of Toronto, where I work on and focus on neural networks. And I graduated in the April of 2021 with a degree in both computer science as well as statistics. Yeah, and that's basically like a really quick about me section. Next, I'd like to talk about a little bit of like an overview about what exactly TensorFlow is and like what are we basically trying to learn from this workshop today. So first of all, TensorFlow is what we call an end-to-end machine learning platform. Now, what does an end-to-end ML? It basically means that we can build, train, and deploy ML models all through TensorFlow. There's no like additional dependencies you have to add or other libraries you have to include to basically kind of do this whole exercise. It's also built on top of this other ML library that's called Keras. Keras is like a simpler one. So you've heard of things like scikit-learn, things like that. Keras is like a more simpler, easier building block that you can kind of stack TensorFlow on top of. And I'm going to be mostly using Keras in our example today because I want to start off with like a much easier introduction, kind of ease you into the harder concepts of TensorFlow. So basically talking about that. A little bit about history. So it was developed by Google and they've kind of open sourced it back in the day. The initial building of TensorFlow was mostly done in the programming language Python, but nowadays you can get like ports to anything. There's C++ TensorFlow, there's like a JavaScript TensorFlow even. So you can learn to use TensorFlow in basically any single language or any platform you prefer. I think that I'm going to use Python because it's what I'm most familiar with and what like I feel that people will be able to follow along the most. So that's basically my choice on what I want to do for this workshop today. All right. So first of all, what is ML? And I feel like, it's best to introduce the concept with memes because who doesn't love memes, right? So on the left, you have like, that meme from, I think it's Family Guy. I'm not sure exactly, but it's like, what is ML? And you take like algorithms and maths and you slap it together. And the second one is like, where would you run ML? And I'm like, yeah, memes are a great way to pick up ML and kind of get started off there. So fun little meme intro. Next, we'll move on to like what exactly ML is. So without sounding too complicated about what ML is, like let's just ask ourselves a simpler question of what exactly learning is. So let's say, you're in university, you pick up a new course, and you're basically trying to figure out like what you're learning from that course. How do you do this? Or you have like an exam. You take some data. Your data is like, let's say you went to lectures, you took notes, you did exercises. That will become your data. And then afterwards, you study the data. That's like you train, you learn from the data, basically use the data to gather conclusions. And lastly, you test yourself. You go for exams, you go for quizzes, that kind of stuff. So there's that whole process in your mind, even as a human being, about how you learn data and kind of apply it. And that's exactly what machine learning is. It also has like the 3 stages, but instead of like human beings or biological systems, we're now going to be using algorithms instead. So we'll start off by, finding data. That's basically your data set, or like what you use to kind of feed into your model. The second thing you kind of do is basically learn from the data. So that's basically what you do by running your algorithms on this data set, basically training them. And the last thing is we'll use that data to map it to unseen context. There's no point in, for example, in like spending all your time learning only about things you've already known before. You got to apply it to new and similar concepts. And that's like the key part of ML too. We should be able to take what our algorithm has learned in like past context and kind of apply it to future data that we haven't seen before. So that's basically the 3 main steps into what I would call like the ML pipelining that we're kind of going to go through today and understand. And yeah, I kind of want to start out from the basic introductions and take it like a bit more complicated. So today I'm going to be focusing on a subset of ML in what we call a supervised learning. So supervised learning means that we're going to have the data to guide us. We'll have like a data set to kind of like make us inform of our decisions and how we're moving forward. And we're going to train our algorithms on these pre-existing data and use it basically. But there's also another thing called unsupervised learning, which is a bit more complicated. I'm not really going to go into, but like it's where your data set isn't as important and you can use like other sorts of triggers to kind of continue your process. So yeah, I'm going to give you like a really quick overview about what like an ML workflow or pipeline is. So like what do you do basically? So the first step is always your data gathering. So that can involve like you going out and doing surveys or you just downloading a data set off like the internet. So the initial thing is, yeah, you need to have data. And what's I think very important in at least in like a work industry settings, not more when you're playing around with it, but it needs to be clean. What that means is that your data set, the format of it has to fit your later steps, your models, whatever comes later. So there's a lot of work in terms of like data cleaning that you would have to do. And the second thing you have to do is then build your model. Your model is like where your data goes into. So you have to look at your data and basically do some like quick observations to kind of pick what kind of model is perfectly suited for your data. And that's like the model picking stage. Next, you got a training. Training is, people like think it's complicated, but it's a very simple, like a single function using a library. Just say, here's my data, here's my model, train it for me. And then usually the pre-existing libraries to kind of take care of that for you. And the last thing, which I think is the most important, is kind of thinking about what you're trying to do. Like look at the model and see how well have I created this? What have I done? What are the different metrics I can use to evaluate how well it is? And can I improve this better? Did I pick the wrong model? Am I using the right metrics? Should I trained it more? Do I need more memory? These are all like the kind of questions you ask at the very end of like your ML process to kind of basically figure out if what you've done is correct. And yeah, if it makes sense, you have good accuracy, good precision, then you should kind of move ahead, publish your results, tell people about what you've done, that kind of situations. Yeah. And again, another meme break, I want to talk a bit more about neural networks. So I'm just going to say that like we're basically today going to take like a bunch of images and kind of try to identify them. And hopefully it won't turn out like these memes. Like hopefully we won't be classifying every single animal as a dog, even though these are kind of cute too. All right, so the last thing I want to talk about before I jump into the example is a really quick overview of what neural network is, because I don't want people to like confuse them with what ML is. So neural networks are like basically a kind of ML algorithm that are kind of modeled upon like the way your mind works. Like a quick biology aside is that your brain is basically filled with a bunch of neurons. And whenever you try to learn something new, these neurons fire back and forth. They send info up and down your spinal cord from your brain. And that transfer information is kind of like what we're trying to simulate with a neural network. So we have in neural network 3 different kinds of layers. So we have like the first layer, which is what we call the input layer. So this is like that. Think of that as like a neurons like right next to like your arm or your finger, like the parts is that feel the stimulus immediately. And then on top of that, you have what we call hidden layers, which is, let's say, for example, take your whole like nervous system or your spinal cord, the part that kind of transmits and does the learning for you. Like between layer to layer, it basically fires stuff, sends information back and forth to kind of allow that learning process to continue. And lastly, you have the output layer, which is basically like your mind or wherever you're getting the final result from. So that's why you do like a bit of computation, kind of change the data near the end to make it more presentable and kind of show that output to people. And basically like that's the whole workflow. If you want later, I can like talk a bit more about what exactly the hidden layers are and like what exactly is happening there. But I think this is like a good introduction so that we can jump into the actual like code and look at it, because that's obviously a better way to learn. So I'm gonna like quickly turn off my screen share and hop over to the notebook. Hopefully you all have access to it. Does everyone have access to the notebook? Could you like raise up your hand if you do? I've also linked it in the chat, so you can just click and follow along. Yeah, does anyone have any issues? Yeah, could you all like just like give me like a quick hands up if you found it? Basically, it'd be helpful for me. Can I?
It's being linked in the chat, so I think everyone has access to it now.
Okay, yeah, I just wanted to give them a second because people were asking. But yeah, I'll go ahead. 1 second. Technical challenges. Apologies. Okay, I hope you can all see my screen and basically follow along. So yeah, so in today's guided task, we're going to be running what I call a classification neural networks, which is we're going to take a bunch of like images and kind of try to classify them in like different buckets. So we'll be using a data set that's called the MNISC data set, but a bit more of an advanced version of that. We won't be classifying like traditional, like usually the MNISC data set involves like classifying like handwriting. So like you take like 0, 1, 2, 3 to 9 and kind of classify that. I'm going to take today like very scaled down images of like fashion clothing and try to classify it. So yeah, let's jump right into. So the first thing we will do obviously is kind of import our libraries. If you wanna follow along with the code, if you can click play to run it, or if you're like on a Mac, you can do Shift Return. If you're on a Windows, you can do, I think, Shift Enter to kind of run the cell. So the first thing we're going to do is import TensorFlow, import NumPy, and import Matplotlib. We'll be using TensorFlow basically. 1 second, let me reload it. But yeah, we'll be using TensorFlow and we'll be using NumPy to process our data and Matplotlib so that I can show you some nice plots to follow along with the exercise. So yeah, this is the data set we're going to be using. You can click on the link to kind of follow if you want to learn more about it. But it's these kind of like small grayscaled out like fashion images, like handbags and like pullovers and t-shirts and things like that. And they're all like really small, 28 by 28 pixels, and you can kind of like zoom in if you want to look at them. Yeah, and then basically we're going to be using that. So let's go ahead and download our data set, which again, you hit run again, it will download it for you. The data set is loaded in. So the first thing we have to do in like any kind of like ML process is you kind of got to look into the data a bit more and kind of see like what kind of data are we getting into. So I'm just going to run the markdown stuff, and basically we're going to then split our data into basically two different groups. There's what we call the training set, which is like what we're going to take the data and parse through to build our algorithm. And then we're going to do what we call the test set. Remember how I said earlier that the whole point of ML is to basically have our inferences transferred over to unseen images or unseen things. The point of that train set is to have a segment of our data that's not passed into the algorithm so that we can know that our algorithm is not basically only working on data, but we can kind of take it to other things. Yeah. And yeah, that's basically what we're going to do. And the images are, if you want to dig into it, they're basically arrays, and they're 28 by 28 because, 28 by 28 pixels, that's the dimensions of it. And if you know anything about images, like we represent like RGB in like 0 to 255. That's like the numerical range for that. And that's kind of how the data will look like if you go into it. And last but not least, because this is like a pre-given exercise, we have our classification labels. So I'm going to be bucketing these like fashion images into 9 different labels. You can see them here, like from 0 representing t-shirts all the way to like ankle boots. And my end goal at the end of this is to basically take any image from that and say, can you tell me what label it is for it, like easily. So yeah, a quick trick that you like to use in terms of like these kind of labeling is you have an array. You just make sure that every index of that array corresponds to your label. Like let's say like it's 0 index because Python, the first one is t-shirt top, and then you can see that mapping perfectly. So that when I can use in my code, I can match it up without doing like any like plus ones, minus ones. It's just like a really good mapping task. But yeah, I want to, like I said earlier, spend a bit more time going into the data and helping you understand what it looks like. So first of all, we have the shape function, which basically tells you like the length of the data set, which in our case is 60,000, and what each index looks like, which is a 28 by 28 pixel. That's the first thing. And then, yeah, I mentioned earlier the length of the data is 60,000, and then we'll look at the labels again, which is a 0 to 9 integer, as you can see here. And it's given in like a UE unit 8, which is like a Python way of saying like an integer. And that's in the training set. Now let's look at what the test set looks like. So we've split apart like 10,000, and we're not going to put this anywhere in our pipeline. We're just going to have that at the end to test on, and that's basically 10,000 images to test on. And yeah, again, length of the test set. Next, let's move on to like more fun stuff. So our network isn't going to run on this basic like 28 by 28 pixels in this basic data set. We need to like change the data a bit more and kind of process it so that it's able to understand. So the first thing you want to do is that the range of 0 to 255 is way too big for a model. Like, we don't want to bombard our initial neural network with this complicated set. You want to kind of make it easier. It's easier for algorithms to understand things in terms of like 0 to 1 ranges because it maps up very well with probabilities. So what we're going to do is basically take our data set and kind of regularize it, shrink it down from that range 0 to 255 to 0 to 1. Now, how do we do that? Yeah, first of all, I'm just going to show you like what an image in this data set looks like. That's a boot. Colors in the 0 to 255 range showing the RGB. So I'm going to regularize it, like I said, by just taking it and just dividing it by 255. That will just make everything map from 0 to 1 perfectly. You have this like nice like probabilistic 0 to 1 mapping of our data. And yeah, another thing we like to do in like the ML world is just create plots. And whenever you're not sure if what you've done is work, just visualize it, put it in a plot. So I am going to plot it out here. If you want to understand this code, basically what's happening is that we're creating like a box of 10 by 10 size. And then we're going through the first 25 images. And we're just saying, can you please render them for me? And that's all it does. You see this stuff about X labels, and that is just me labeling this. So this is basically, even after dividing it, just to make sure that we haven't lost images, and this is what they look like, what their classification include. Like, yeah, they make sense. That's an ankle boot, that's a t-shirt, that's a dress, that's a sneaker, etc., etc. Yeah, so now we've gone through the data, we've pre-processed it, we have everything in this nice 0 to 1 classification. We have what they should be classified as based data set, like what kind of an image is this. So now all we have to do is basically build our model, train it, and see if it works overall in the end. And that's what I am going to do now. So first of all, let's start building the model. So how do we do this? Remember how I mentioned earlier that a neural network is based on layers? Each layer will kind of like do inferences for you, whether it's starting or end. So I'm going to keep this simple and just have 3 layers. A very simple initial layer, only a single hidden layer, and your final output layer. And we'll be using Keras again for this. We're going to use a dense layer, which just means that we're packing the neurons more closer together to give us easier inferences. And that's what I'm doing here. So people think that like modeling itself is a very complicated process, but with all the work done in TensorFlow or like in our APIs, it's pretty simple. So all we have to do is basically set model equal, call the library tf.keras sequential because our layers are coming one after the other. So we keeping it sequential. There are non-sequentials where you can like split the layers apart, put stuff in the middle. So that's what we're going to do here. And then our first layer is flatten. So what flatten does is it kind of takes the images and based on regularization, compresses them into that 0 to 1 range I was talking about. Then you have the second layer, which does the inferences. And you see this thing called activation. That's something I can elaborate upon later if people want, but that's what we call an activation function. If you want to understand them, just think of like a light switch. So your light switch turns on when you give it, like when you press it. In a similar way, a neuron is only fired when the input reaches some amount of money. So some amount of like a trigger. So what basically this means is that you have like you think of like a graph, and it's like 0 until below a certain input. And then once you hit that input layer, it just shoots up to 1. And that's basically kind of similar to what we're doing here. We're saying that when our data goes through these layers, we want some of it to be held back, some of it to be passed through depending on how we're training it. Yeah. And yeah, I'm now just gonna go ahead and compile the model and add it in. So we're gonna give our model a couple of settings. So we have these things called optimizers, which basically kind of speeds up the process for us, because otherwise our model training might take like a long time. It just like goes deep inside like the back end of the model and kind of like stacks stuff, moves neurons around to make it easier for us. And then second of all, we have a loss function. A loss function basically tells you like how much of the data is kind of being lost in between layers. And it's a way for us to kind of like measure what's going on. And lastly, I'm going to give it the metric called accuracy. Accuracy is basically saying we've taken our model, trained it on like a set, and we're going to eventually make it classify new kind of images. Among like these new kind of images we classify, how much of it is correct, how much of it is wrong? And that's like a very key way you want to evaluate your model, because it tells you like how good it is in terms of like dealing with new kinds of data. So that's basically what I'll be doing in this last like metric portion of it, to kind of like tell people like, yeah, that's what I'm looking for here. And then let's go ahead, let's train the model. So all we have to do here is call a single function and feed the model. But I'm gonna like, again, repeat what I said earlier, that we've kind of followed all the steps we have to do. We've cleaned our data, we've regularized it, we've put it in the right format, and now we can just feed it in and say, hey, train it for us. And for training, all we do in TensorFlow is call model.fit, and we give it the training images, which is like our data set of the images, the labels, what they should be, and epochs. Epochs refers to the number of times you kind of like sending it through the layers. So I'm going to have 10 epochs here to say I'm going to run it through 10 different times, and hopefully you give me the best accuracy. Like the number of epochs to use is kind of like a thing you figure out by kind of like adjusting it up and down to see what gives you the best result. And I've already played with it, so I've come to the conclusion that 10 is the best. If you want to like explore it for yourself, just change the number from whatever you want, like 1 or 2 or 3, and then rerun the model again and see how your accuracy changes as you go through it. So yeah, I'm gonna continue with 10. And you can, just 1 second. I might have forgotten to run some stuff before, sorry. Yeah, if you miss like a box here, then when you get to the one below that, Collab won't be able to like know what's happening there. Okay, now it should be fine. So yeah, basically you can see the numbers here. It tells you how long it takes. It tells you how much is lost, like 49% is lost, 37% is lost, 33. And what you see as like the number of epochs goes higher and higher, losses will get lower and lower, and your accuracy will go higher and higher. And that's exactly what we're looking for. We want our model to get better the more times we train it. I'm just going to let it finish. Ta-da! And yeah, it comes up to around a 91% accuracy, which is basically what we're going to now reevaluate based on the test set itself. So the way we're going to do this is basically run models that evaluate, which means we're going to give it the test images, test labels, because the model was trained already, and kind of see what the loss and accuracy is on that, to kind of just verify what we've seen before. Yeah, and then it comes up to like an 88% accuracy. And you can see there's a difference between the 91% here and the 88% here. And this difference in accuracy from like what is on the training set and the test set can be attributed to this thing that we like to call overfitting, which means that if your model is overfitted, it means that it cannot deal with too much external input. It's only hyper-focused on the data you've already given it, and it's not able to recognize future data. So our model might be a little bit overfitted, but 88% is by far and above an amazing score on any model. So we don't have to worry about that too much. I trained stuff where it's like more of like 50%, 60%. Then you have to worry about like, oh, have I picked my data set in the way that it's like a single kind of feature, or images look exactly the same way. So it's a good way of telling you that like basically you've kind of gone wrong in the data cleaning, data preparation part of it. You should kind of like go back and like fix that stuff and like re-go over it again. And then yeah, you train the model, you have your accuracy. What's the most important part? Let's use it to, make some inferences. Can we give it a new random, like small, like fashion image, and can it tell us, like, is it a boot? Is it like addressed correctly? So the way I'd like to do this is basically our model. If you go in and basically print out like what the output looks like, is what we call logjits. Logjits are basically like TensorFlow's way of like representing model outputs. The thing about is that it's not super useful to us in this format, because I feel that it's easier for people to understand probabilities, like a 0 to 1 chance of stuff. So I'm just going to take that and use what we call softmax. Softmax just converts the logits already into very simple probabilities. So that's just like a simple conversion of our model into something that's easy to understand. Let me just run that. And then I'm going to call predict on it. So the results of this are not going to be weird logits. They're just going to be probabilities in that, given this image, what is the probability of it being category 0 to 10? And that's kind of like what our array is going to look like. Sorry, I didn't run it. Stop again. There you go. Here you have the different probabilities and what it looks like in your 0 to 9 array. And yeah, if basically the highest number among this would be what our model thinks the image is, which in this case, you can see it's labeled 9, which if you go up and check refers to, we think it's an ankle boot. Sorry. And now we go back down and yeah, let's see what it was like originally. So in our data set. So it's a 9, it's a 9. It matched. Congratulations. We were able to predict what it looks like. So here this complicated piece of code here basically is just me going through like a bunch of the labels and kind of like visualizing it out for you and showing it how it looks like. So let me just run this first to show you like what it looks like. 1 second. Yeah, I'm 1 second. Sorry, yeah, this piece of code is basically the code that drives this plot. So I'm gonna plot this out first. So what I'm doing here is I'm again splitting the labels, creating a grid, giving it an X and Y axis, saying that I want to show these images in this kind of format. And then basically I'm using 2 different kind of colors to say if it's correct, I want it to be displayed in blue. If it's wrong, I want it to be displayed in red. And then this function basically just goes through all the labels and kind of assigns them to red and blue so that in the next section you can see very easily if it's right or wrong. So yeah, I'm just gonna run this on a single thing. Is our first image correct? Like, yeah, it says ankle boot, it's 100% ankle boot. Easy. Our model worked correctly. Now let's see like what happens if I give it a different data set. Now we see here that it shows up as number 8, which if you go back up and see there is 1 second, a bag. Now this is clearly wrong. We're looking at a sneaker. We're not looking at a bag. So that means our model classified this wrongly. And this kind of numbers here also show how confident the model is about its results. So you can see that our model was like not super sure here, kind of like, okay, it could be 5, it could be 7, it could be 8, but I think it's mostly 8. And then it came up with it wrong. So to kind of illustrate this, like the model can be confidently wrong. I'm going to show you a bunch of plots of the different things and show you like how that breakdown looks like. Yeah, so if we're going to go through it, you can go through it. And I'll scroll down to, so it's an ankle boot 100%. You can see it's like initially super, super, super sure. And then you get to like the bag and it's just like, oh, why did it get so wrong, basically. But yeah, usually when the model is like confident of a result and it's like overwhelmingly that it should be right, if you have this kind of like split between different kinds of categories, there's a good chance it misclassified it because it was kind of confused with the input it got. Yeah, even the code a little bit, but it's pretty much overwhelmingly correctly classified. Yeah, and now this is more of like me showing you taking different images and kind of like putting them through and showing them like how it classified. So yeah, I'm just grabbing an image from here and I'm basically going to classify it. Comes up as 1, and let's see the label for it. It's a pullover. And yeah, that basically is the details I've included here are basically more important details about like Keras, in that we're trying to test a single image here, but the actual Keras like library is optimized so that you can do a batch. So if you want to do a single image, all I'm saying is that you just have to use a batch and give it 0. Well, regularly you're going to do this in a full data set. You can just go ahead and use it the way it is. So yeah, it was predicted correctly. So congratulations, and that kind of is the overview of the whole thing. I kind of gone through like how to take a data set, how to clean it, how to train a model, how the training process looks like, how to like basically kind of test it on different kinds of new data, how to evaluate its accuracy, and kind of showing you like different kinds of like positive and negative classifications of the data. So yeah, I'm going to 1 second close this and swap back over to my slides so I can just give like a last bit of like final thoughts and open it up for Q&A. 1 second. So yeah, I like to share like a bit of final thoughts. That I just want to say that this workshop might be focused on TensorFlow, but there is a bunch of other interesting libraries out there for machine learning. You can use scikit-learn, you can use Torch, PyTorch. There's so many different things to explore. They kind of all work under the kind of concepts introduced today: cleaning data, putting it through a model, evaluating it. So I think like that's a more important skill to master than what library you're using. I also want to I've included a link, I think, on the Hacker package about a link to the actual TensorFlow API itself, and you can look into more advanced TensorFlow things. Like, for example, the concept of what exactly a tensor is. Which is something that Google took from physics. It's like a more complicated array, because you notice the arrays that we use are from NumPy. They're just like straight up numbers and images, but there you can give it complex numbers. You can give strings in the same kind of like array and kind of use that to kind of like, classify your images and do that. And yeah, there's machine learning world is like an extremely open one with like really worked on things like online learning resources and like things you can go easily and learn from. And yeah, feel free to reach out to me too if anyone likes to chat more about like different careers in ML, how to explore ML as a career further. And yeah, thank you. Thanks so much for coming, and I'd like to like open it up for any questions. I see someone asking like, is this what's working behind jobbing websites? Kinda. I used to work on like recommendations and like some of my different internships, and they use like these kind of models basically to kind of like go through, take a user search data and apply it to kind of personalize stuff for you. I think if you want to ask a question, you can also like come up to the front of your room, and like then you'd be able to address everyone if anyone has any questions.
Sorry, just to clarify, if you want to ask a question, feel free to raise your hand or, sit in like the blue chair. And then once you do that, like if you start speaking, then you'll be broadcast to the entire room.
Someone asked me, how would you improve the model if it was inaccurate, like the bag/sneaker example? That's a very good question. So usually if you spend time like going through different kinds of like models, we have like what we call like an acceptable accuracy limit. Like for these kind of tasks, I feel like the 10% misclassification is usually fine, as in it's something you can like deal with on the back end. So like if you were going to turn this into something you'd actually use in a product, you would have like something at the back that goes like, hey, we caught these things wrong and fix it. Because no model is 100% accurate. There's always going to be things that are going to be different and hard to classify. So the way you would deal with it is basically just dealing with that as it comes and fixing it in terms of like other code on top of the model. A better question would be like, what if the accuracy wasn't what you expected? Like if it's not like what you wanted, then I'd say you have to look into like other different kinds of models. Like I picked this one because I've already looked into it. I knew it was the best for this kind of example. But you should have a phase before you start modeling where you like try out a bunch of different models. Just take like a data set, chuck it into them really quickly, come up with like a quick accuracy metric so you know like what kind of model fits your data set. And as you do this like more and more and more, you have like a mental mapping on like what kind of data suits what kind of model. Like we were using classification, which is like a problem very used for like neural nets are really good. You can use logistic regressions where like because our answers are in like a 0 to 9 kind of like numbers, right? There's also problems where like you can basically take the data and you want to give it like a single number. Like let's say like there's this exercise I did once that like lets you predict housing prices. Like let's say I want to know like what the housing prices is on a district. That's a different kind of output, right? it's not like a bucket. It's a straight up like, can you tell me the price? Those are different kinds of models. As you can use like a more traditional like linear regression, things like that. So it's just a lot of like experimenting, getting to know like what kind of model suits your data the best.
I also have a question.
Oh, go ahead.
You know how you mentioned that you guys use like machine learning for like users data to like give recommendations. So when you're training the model, are you also able to see the user's data?
Oh, that's a good question in terms of privacy. In the companies I worked at, we usually get our data like salted in that I can see like people's like their user ID internally. I don't know who you are as a person, and it doesn't really matter to me. What's more important to me is basically like what I can learn from the data. So when the work I do is just mostly I'll just take that data, clean it, and put it in. I don't need to look at I don't focus on individual people unless you're outliers, in which case I still don't know who you are. It's just that I'm interested in the fact that like why do you not fit my trend? So yeah, it's not like I know privacy concerns are a big thing, but if you want to work in this field, you have to deal with some amount of data, and just trust that if you work for an ethical enough company, they're always going to give it to you in the form where you cannot tell who it is.
So like you can see the data, but like you don't know like the person's name or anything.
Yeah, you don't know the person's name. You don't know like where they're from. You can see like I used to model things like I was working on a model once at my previous co-op where we were looking at ad spending. So like basically if people spent money on ads, like how effective were they? So I could see things like how much money you spent on your ad campaigns, what were your returns. So only things that are relevant to basically what I'm trying to model. Does that answer your question?
Yeah, that answers. Thank you.
Someone asked, for an ML position, what do people usually do? That's a really good question, because I'd say like ML is one of the tools in the broader like data science world. So there are different kind of positions in there. There's like a more traditional role of a data scientist where you might do some ML, but your job is more of like, hey, I have a data related problem. Can you fix this for me? So you might do things like making reports in SQL, presenting data in a way that's understandable. And the modeling you might do is like heavily focused, at least in the tech industry, in what we call like A/B testing, which is like when you have a product and you're trying to release it, you want to know how well it does. And you like kind of, in like a high school experiment, split it into like your control group, your test group, and then evaluate what group is doing better. And in that process, you might do some ML modeling. And then they're like hyper-focused, like ML engineers or like research scientist positions that usually you might have like require like a bit more grad school positions. These are the kind of people who actually go out and build new models. They're the people tasked with like, hey, we have this like interesting new problem in our organization. We don't have like a pre-existing model for it. Can you go look into, read some papers and come up with an actual model? So a lot of the work falls into the former category. It's sort of like, taking pre-existing models and fitting it and coming up with conclusions and putting it in a way that people understand. That's a lot of what your job involves. Versus like the latter is like a bit more specialized and a more of like a research, like kind of like you might have to go to grad school to kind of like come up with new models. So yeah, I hope that answers your question. Does anyone else have any other questions? Oh, someone asked, can you create your own model or the image library? I'm going to answer this based on my previous answer, in that if you're in a position lucky enough in like an organization where you're building new models, then yes, you're going to come up with your own library. Like TensorFlow is built by Google. If you made it into like a research position at Google, you can definitely add stuff to TensorFlow and even contribute it to it in an open source manner. It's definitely something you can do. But usually for most tasks, we don't want to go out and reinvent the wheel. We have people who've hyper optimized this stuff for us, made sure it's quick. So it's much easier to use things that people have already made. And your focus is instead on like, am I using the right task for the problem? Am I using the right tool for the problem? Then is that tool good enough? Because it's usually been tested very well, gone through several iterations of like very smart people who've written that code. So yeah, if you want to look into like positions where you get to build model, I definitely like consider going to grad school or like getting a lot stronger of a mathematical background. Definitely. Anyone have any more questions?
Yeah, I have one more question.
Go ahead.
Remember like when we were I forgot which part it was, but there was like where you divided by 255, like to get it 0 and 1. I'm kind of confused. Can you explain that part again?
So the model I picked basically it wanted its input layers in the form of like, it basically wanted them to resemble probabilities because this pre-made one from TensorFlow expects data in that format. So it's just basically me saying like, hey, I have images, but my network itself can't take a full image and treat that as like data. So it's much easier to just divide and make it standardized so that my network can understand it. So that was all that dividing by 255 does. You have to do this very commonly in that like your data usually is going to be like some large number, and a lot of the ML models, they're based on like probabilistic models, so they expect a probability. How do you get a large like number in probability? Just divide it by like the largest size of your data set or like the largest pixel value. So that's like a very common process you'll have to do.
But like, why divide by 255 specifically?
Oh, 255 is the maximum RGB value for an image. 0 to 255, if you remember the range I showed you.
Oh. Thank you.
No worries. Anyone have any other questions? Oh, someone asked if I want to get into the ML industry, where should I start? That's a very good question. Like I can talk a bit about like how I started. So when I was in first or second university, I kind of decided that like, hey, I did some exercises. I want to look into this. Let me go look for internship positions in the ML role. And the only real job I could get initially was to start off as a data engineer. So I started off work doing like data pipelines and cleaning data more than training them. And then in my later and later co-ops, I went on to be a data scientist. So I'd say that if you want to get into the industry, I look for any role basically, because initially you won't have the experience or the cutoff to maybe make a data science role or a machine learning engineer role. So I'd say get your foot through the door in anything data related. Like if you're working as data engineer, data analyst, that's like a perfect way to start. And then after that, kind of like market yourself to companies and saying, I already have this experience in data and I've already done all this like work. Can you now hire me data scientist? Oh, another thing I kind of want to mention is like another good way is just do side projects. I want to plug a website called Kaggle.com. It's where you can go and basically download data sets and kind of play with them and make models. So definitely spend your time, like put stuff up on GitHub, do as many side projects as you can to show like employers that I know what I'm doing. I love the ML world and here's like a bunch of past experience. But the one caveat I'd say is you're looking for the positions that involve like very hyper like ML work, like, you know, like building libraries. I think you have to eventually go to grad school. And an add-on caveat to that is that the work I showed you today is like kind of very high level. I didn't really go into the super much details of like what the layers are doing or things are doing. If you want to understand that, I'd recommend like either in college or on your own, developing a better mathematical background. Exactly. So sure, I'll keep it Waterloo specific. So in Waterloo, in first and second year, if you're in the math department engineering, you have like courses in calculus. I'd say take the third series, so don't just stop at Calc 1, Calc 2. Make sure you take multivariable calculus because all the data here is multivariable. They're in large arrays, so I'd start with that. Another thing that I pursued, which is kind of challenging, but it's an idea, is to also like look into like doing a minor or double major in statistics. I double majored in statistics, so that was a good way of getting understanding of probability, regressions, and more like advanced like ML modeling. And when you hit third or fourth year in Waterloo, you have access to like a third or fourth year CS courses. So there's a bunch of them. There's CS 480, which is Intro to Machine Learning, which is basically goes over like how to do ML things specifically, ML algorithms, how do you train them, develop them. There's CS 486, which is Intro to AI, where you don't just focus on ML. You look at the broader world of AI. You do things like more about regressions and things like learning how like even like how graph search algorithms work, because they're all artificial intelligence. And there's another two. There's a course offered in an options course that comes up like once every 2 years called neural networks, where they just go super deep into like what I've taught you, all only focus neural networks, all different kinds of this. And there's a last course, it's called CS 45, which I think is the mathematics of machine learning or something like that. It's a course that basically teaches you like what is the math behind machine learning. You don't do much coding in that course. It's a lot of like mathematical proofs. If that's up your wheelhouse, you can look at these courses once you get third or fourth year. But for your first 2 years, like in Waterloo, if you're in like the math or CS department, you usually would just be doing like generic like CS courses that build your understanding of like operating system and data structure. So yeah, if you get a third or fourth year, I definitely look up. Is it worth it to do a minor? I think so, because doing a minor in CS gives you access to these courses. If you're already in CS and if you're looking at a minor in statistics, I recommend it super much, because I feel like you'd have a much better mathematical understanding about what's happening in this kind of like models. One last minor I want to plug is at Waterloo, we also have a really good combinatorics and optimization department. A lot of the learning behind ML is kind of like a CO kind of optimization problem. So if you're looking into that, I also recommend like taking like CO 250, the intro optimization course, and seeing if you like that. So yeah, if your end goal is basically to I want to work on building models, I'd say like spend your undergrad like doing as much math as you can. If your goal is I just want to use them, do cool stuff with them, I'd say continue doing what you do. You can learn all of that outside of the school. You can spend your time playing with data sets. You can definitely be an effective data scientist without having to hyper focus on mathematics. So just pick your path, decide like what's more up your wheelhouse. If you like math, go for it. If it's like you don't really want to spend all your time doing like a lot of boring proofs, you either like look at like build models and see like the fun visual aspect of it. I'd say like keep your interest in side projects and more like learn from your internships or like that kind of stuff. Yeah.
Are there like data scientist jobs that involves using the machine learning models, but like not actually knowing the math? Because I don't think we could do it without the math.
Oh, 100%. The math is only really necessary if you want to be the people who are actually building the models. Like if you want to go develop a TensorFlow equivalent, or if you want to go out and like build a new model from scratch, I think it's good to know the math because you can't use pre-existing stuff. Most of the jobs out there are exactly what you said. You don't need to know the math. You can just be a data scientist who knows what type of model to use or what kind of data and how to evaluate it. That's more of your skill set, right? So like looking at this data set, what kind of model is it? And you spend all of your time like, how do I make this better? Can I clean my data better? Are there better metrics that can use to evaluate it? So it's not a field that requires very intense math beyond like some basic understanding of like probability and statistics, which I feel that like anyone can pick up online or do an online course in it. So I don't want to like discourage anyone from pursuing this field and thinking it requires a lot of math because it does not.
Okay, thank you so much.
No worries. Does anyone have any other questions? I'll give it like a minute or two. Someone asked me, is this how Alexa plays Despacito? I mean, kinda. I mean, that's more of like a natural language processing thing layered on top of machine learning. But yes, that's basically kind of how it works. Yeah, if there's no more questions, I guess I will end the workshop today. Thank you all for coming. I hope you learned something, and I think you guys have my contact information. If you want to learn more about the field, I'm free to chat with anyone. I'm also like around here as a mentor for this weekend if you want to talk about ML regardless. So yeah, I hope you all had a great time, and thank you all for coming.
Oh, I have a last